Well, we made it, folks. We can now get started. Also, congratulations on getting through the second exam. These are pretty intense, but I feel like by the time you've done the second exam, you've got a good feel for what each one of these are going to look like. I felt like on exam one, my exam wasn't as close to quizzes that we did in class that I would like, but exam two is targeted pretty closely to the quizzes. And that was my real intention. That's what you're going to see on exam three and as well on the final exam. So as far as exam three goes, it's going to start in chapter seven. I posted this quiz just a little bit early. It has the same due date, a week away from Thursday. But that quiz number seven problem is based off chapter seven, which means it's basically what your first exam question is going to look like. So you'll want to get this solved as soon as possible, just because it's easier to solve these quizzes when the ideas are fresh in your head, then it solidifies the knowledge. But once you go to study for exam three, this would be the one you'd want to come back to. But we're going to redo everything for exam three. When we get to kind of close to this week here, we'll post out the information, chapter seven through wherever it makes sense, the same kind of versions of the sample exams, and I'll call for questions on the Thursday right before the exam, and we can have a mini review if we choose to. So I'll be grading the exam two. It's nearly done. I just have to enter in the grades. I'll have them uploaded to Canvas pretty much first thing on Thursday morning, and I'll hand them back to class when we return tomorrow. Any questions at the moment, folks, with any of those announcements or otherwise? Okay, well, I just want to say with what I've seen so far on grading exam two, people did really well. So statistics does get tricky. We're getting into inferential statistics, but keep on working like you're working, showing up to class, getting through the quizzes, the homework, participating in class. It's really just going to be more of the same. No matter how complicated the formulas go, one of the things I really like about this class, the 4 credit one, I always request to teach this one, is we really have the time to really delve into those formulas, see how every single piece works. And it's really just going to feel like more of the same. Maybe the formulas are a little bit scarier, but you'll know where everything goes, how to make the right interpretations, mentioning the context, just the same kind of stuff we've been doing all along. As far as we're going so far, we're going to finish off chapter seven and the additional example. Chapter 10 is kind of like a bridge between what we've been doing, what we're about to do. We'll talk a little bit about randomization, a couple kinds of studies and statistics, surveys versus experimental designs. And then we're going to move into chapter 13, starting on inferential statistics. So here's where we left off on Thursday, almost a week ago. It's kind of rough returning to this because it wasn't on the exam, and that's been our sole focus for a little while. So let's refresh ourselves. The idea here is the Wright meter is just a measurement of lung strength, how well a person is able to push out a volume of air. It's a pretty big device that we saw. It comes with a suitcase basically. And so there's a smaller device that's not as accurate. It looks like it's biased in a certain kind of way, but it's just useful for if you're having to pack light, if you're forced to. So we use these data. The mini Wright meter was the explanatory variable. The Wright meter, the full device, was the response variable. And the scatter plot looks like this. We modeled that scatter plot with the least squares regression line, this y-hat version right here. So now doing this, we can make certain predictions. If a person using the mini Wright meter had a score for their lung strength of 500, is what part B asked, the predicted official value that they would have given is found by just putting 500 right in for X on this y-hat equation. We'll build a new y-hat equation on our additional example after this one's finalized. So we plugged 500 in, we got the 495.95, and this 495.95 is the so-called predicted value. Predicted value. It's a value right on the line itself if we were to have plotted it. The next part is a little bit trickier, calculating the residual. But any questions so far about the predicted value? Okay, so the residual always has a particular formula. It's E is just the symbol for residual. The real meat of the equation is this. It's tricky because you have to know what did we mean by Y? We mean this Y right here, the actual observation. So The residual is the observed value minus the predicted value. Y hat is always connected with the predicted, and we calculate a predicted value 495.95. So take what's observed in the data, subtract what's predicted. Let me fit the word predicted in there a little bit better. Put in what's predicted by our regression equation, y hat. And the difference between those two different values is what we mean by the residual. The residual was negative 19.95. That just means that the predicted value was lower. So, excuse me, higher, got that backwards. The observed value was lower than the predicted value. That's pretty much where we left off, calculating the residual. We did look into one additional thing, looking into whether the y-intercept makes sense as an interpretation, but we skipped across the slope. So that's where we're at so far. Yeah, go ahead.
How did we find the, I probably just missed it, but how did we find the 120.95 and the 0.75?
Oh yeah, that was when we went over to the calculator. We would stat, edit, and it looks like I have different data in my calculator. But once we have those two variables in this form, we hit the stat button again, moved over to calculate and hit option 9. It was option 8 on this one. Yeah, good call for the scatter plot. That one's the option 9 under zoom here. So option 8, the linear regression, gave us, after hitting enter a bunch of times, the A value and the B value, and we just put both of those together.
Okay.
And we'll do that again on our bonus problem, I guess we could call it, the additional example next.
Then we just put, and then gives you the formula at the top, right?
Yeah, so it's kind of nice in a way. You just put in whatever they say A is, whatever they say B is, and you copy that down directly on paper.
Thank you.
Yeah, absolutely. It's been a while since we looked into this. Thanks for asking about that. Other questions at the moment? Okay, so this is pretty much the big calculator exercise that's going to show up on exam 3. It'll be like the first example. It'll be something like examples 1 and 2 in these notes, or something like the additional example we're going to look into, or even the quiz problem. Just a different context, different looking data, but same kind of questions. So let's go down to this part where you didn't quite get to. We skipped over this one actually, so we're finally getting to it. It wants a practical interpretation of the slope using the context of the study. I find this question is really tricky, especially because MyLab statistics, it's all multiple choice, which is kind of dissatisfying. The math department doesn't want us to give multiple choice exams, so it's really just kind of a practice when you're in MyLab statistics. Going from the multiple choice problems to doing them on paper does feel different. In multiple choice, you're just looking for what's wrong. But on paper, there's certain things that we're really looking for. So the first thing we want to think of is, when you write down this line again, this is just a screenshot from above. The first thing that comes up, this term, this is the y-intercept. The second term that comes up, the one that multiplies the variable x, the explanatory variable, this is what we meant by slope. So we're interpreting that number there. Let's connect that with some color coding. So first thing you might want to do, and kind of a step-by-step process, let's actually write out these steps because it does feel like a process interpreting the slope. The first step 1 I would take on doing this is just to rewrite the slope. Slope is equal to 0.75, but you turn it into a fraction and you make it quite long because we're going to put it in units. The denominator is always going to be a 1, whatever the number they gave us is divided by 1, and you get the same exact value. And now for step 2, we plug in units. Step 2 is units. And there's a definite order to this. The numerator units is the response variable. So I'll just say briefly, instead of numerator, you could just say top. I think that's a nicer word. Top, use units for response. And for the bottom, the units is for the explanatory. So that means we might want to scroll up and down just a bit. Let's grab this as just as a quick screenshot. Plug that down below just as a reference. So the units for this are going to be, the response is column 2. So we'll have 0.75. And what should we call this? This is really a score for the right meter. We might just briefly just say right meter score. I think if you just said right meter, that would have been fine as well. I'll call it a score. The explanatory variable is the first column, the mini right meter score. Kind of a long unit on this one. So if you left off score, definitely no big deal on that. It always goes together in that kind of way. It's the horizontal axis, the mini right meter. Vertical axis is the right meter. Vertical axis goes on the top, horizontal axis goes on the bottom. Or you can just think in terms of response over explanatory. Any questions about that so far? It might not be a bad idea, just make it a fraction. That way it kind of compares with what you see on both sides.
You scroll up
Yeah,
to another problem where we did given practical interpretation of the slope of at least squares.
yeah, here's the one on part C that we're looking into.
Is this one different than what we're doing right now?
This one's the same. So we have the unit for we call that Y variable, but the Y variable, this is what's tricky, right? The Y variable is also the response variable, and the X variable is also the explanatory variable. So coming down below, yeah, we set it differently. We have the response here. Let's compare the two by saying Y variable, just specifically, so it feels compatible, over the explanatory, which was the X variable. Bar for variable. But let's look at that just one more time because that's kind of a nice visual. I actually have the axes here that's printed off with the names. So when you go with slope, it's always the same process. Take whatever the number is, gather the sign. So the negative was important on this one. Numerator is the unit for the Y variable. Let's add to this response. Denominator is the unit for the X variable. Let's add to this one explanatory. And the explanatory variable, which is the X variable, is the one on the horizontal axis. That's tricky because that's like 3 ways to say the same thing. Horizontal axis is the X variable, which is the explanatory variable. It feels like information overload, but it's just because we're thinking about it in several different ways. The plot versus the variable versus the role the variable is taking. Then the numerator was net growth rate, the Y variable, which was the response variable. So this is a good one to come back to, particularly say you're doing quiz number 7, because again, interpreting the slope is always a pretty tricky process, I'd say. Other questions at the moment?
So going back to the one we're on right now,
Yeah.
would it be, no, you're good, I just,
I kind of cut off the explanations on this one as well on my screenshot.
you're good.
Let me pull in the full screenshot just for the better visual. Goes about like that. I think this one's extra tricky too because mini right meter and right meter feels the same. Oh, don't want to flip it. It feels like the same variable, so it's kind of already just kind of like a mentally foggy thing to look at. Feels like we're saying the same thing at once. But other questions at the moment, looking into those? Okay, thanks for the questions so far. Those are exactly the things you want to be thinking about in interpreting this slope. And that's step 1, step 2. Step 3 is the interpretation itself. But it always goes kind of the same way. So here's how I'm going to format step 3. We talk about a 1 additional unit increase. So we'll start by saying for each Well, the unit is a point, so I'll say for each point increase in, and I'm gonna just put a blank here so we can see it as a structure. What goes down below here is going to be the explanatory variable. So for each point increase in, we just have to say what the explanatory variable is. Here's the next blank. We have to put in the whatever the response variable is. It's either going to go up or down. It depends on the sign here. We don't often put a plus here when it's positive, but let's put it here just so we can make the connection. Due to that positive, we'll say the whatever response variable is will increase by, and then one last blank. We'll just say whatever the slope is without the denominator. So this is the structure each and every time we go to do this problem. In fact, when we go to do the additional problem, we'll emphasize that by just screenshotting this and plugging it back in. So essentially what we're saying is, let me get the colors back together. For each point increase in the right meter score, increase is going up or down. It's in the vertical direction or the y variable direction. So in the right meter score. Oh, hang on. I got that mixed up already. It said explanatory variable, right? And I grabbed the top right meter score. That should have been the mini right meter score. Let's start over. That was meant to help me out on that. Yeah, go ahead. Yeah, absolutely. That's what this problem over here, the extra example is going to be all about. We'll do it from top to bottom. And I agree, it's been a while. Yeah. Other questions at the moment? Okay, so my mess up on this one was, and it's tragic because I had the guide, right? I should have just followed exactly what this said. But when it says for each point increase, that 1 point increase, that's going horizontally. From what we did before up here, we said for 1 point increase, the number of grazers, that's going this way, one to the right. The net growth rate, the numerator, went down by 0.91. So I want to talk about the denominator, go bottom up basically on this next one. So following this process, we got it right on this one. Here we have a guide, and I still got it backwards. I want to say for each point increase in explanatory variable, the mini right meter score. Now we talk about the response variable, the right meter score. This is a positive value for the slope, so we have an increase, and it increases by 0.75. So each time a person has one score higher, when they use the mini rate meter device, their official score goes up by 0.75 is what this is all saying. It makes sense because it's going up. We're just saying move right by 1 unit, we go up by 0.75 to get back to the predicted line. This is the one going horizontally, 0.75 is the part going vertically. That's a tough problem. So again, we'll definitely redo this one on the next problem. But any questions so far, just seeing it kind of as a step-by-step structure and a guide? Okay. The best thing is always look at a picture. That's one of the things I didn't quite like about this problem. The scatter plot wasn't plotted. The next problem we'll do, we'll actually have the scatter plot plotted so we can see how this all connects. Well, we're just about done with these notes. The next thing we interpreted was the y-intercept, but This was kind of a funny problem. The y-intercept, like we mentioned, is always when x, the explanatory variable, is 0. So we just thought about what was the context. Explanatory variable is the mini right meter, and if that goes to a 0, that means the person has no respiratory function whatsoever and became a medical emergency. And that means it doesn't even make sense to say what would the value be for the right meter. It should be 0 as well, for example. So sometimes the y-intercept makes sense. It did in example 1. Other times it doesn't. It's always kind of totally up to the context. Last thing is part F, where it says, explain why we should not use the least squares regression line to predict our right meter score from a mini right meter score of 250. Here's what they're trying to say. If you're making a prediction and you have a value 250, all you're doing is you're plugging 250 into this original equation over here. That's exactly what we did in part B. We predicted for the right meter score of 500, the bigger device had a score of 495.95. And that was a valid prediction. But for some reason, you cannot do the same if the right meter score is 250. You should not. You could plug it into the equation and get a value out, but it's not guaranteed to be sensible anymore. Anyone recall what the problem is with the value of 250?
It's too far off, right?
Exactly. It's all about that explanatory variable. The mini right meter scores range from a value as little as 346. That's the minimum value on this. But this is way below even that minimum value. In other words, if we try to put 250 into the scatter plot, we have a point that's over here, basically. Maybe kind of exaggerated. I don't have units to tell for sure, but it's way, way from the main grouping of the data. I can't necessarily say the line continues beyond where the actual data values are. If we try to make a prediction too far out, we're now extrapolating. So that's the whole problem on this one. We can say really briefly, since the minimum for the mini right meter values is 346, unless you spot a smaller one. I think that's the minimum on these data. 250 is far outside of the range of data. And there's a bunch of rule of thumbs that go along with this, but usually if this was an exam question, it'll be pretty obvious it's well outside the range. So since it's outside the range, making a prediction for 250 is called extrapolation and should not be trusted. Essentially, we'd have to redo the experiment and somehow include people with low values of 250, but that might include maybe small children or people who are ill. That might not even make sense to do in the first place. But that's the main takeaway from the last problem over here. In fact, you could have said that in part E. 0 is way outside the range as well, so that's considered extrapolation. When we did 0 for our intercept on the last problem, there was a data value for 1, so it was reasonable to say that's nearby our data. It was an extrapolation in that case. But that's the wrap up of the official problems that we looked into chapter 7. Any last questions at all before we take a look into that additional example? Okay, let's take a quick break while this saves and closes. Now we're on to this extra example here. After we get through this, we'll take a look into chapter 10, but it seems like we'll probably be finishing off chapter 10, maybe starting section 13.1 on our Thursday's class. So here's our next bit. The extra example, and I'll overwrite the files here again with our solutions. This is in the blank lecture notes as well if you want a blank copy. And I like the problems in this format better because I feel like if you're doing regression, it's nice to have the output you're actually looking at, not calculator output. So here's the new situation. First, it comes with some terminology. Looks like this is another medical field kind of a problem. Any medical item used in the care of hospital patients is called a factor. So factor has different meanings in different places, but for medical science, that's their definition. Example of factors can be intravenous tubing. I don't like to visualize that. Intravenous fluid, needles, shave kits, bedpans, diapers, dressing, medications, code charts even. All these are considered factors, probably even the Tylenol that they might give you during your stay. So that's any medical item whatsoever. I'm not sure if Tylenol, well, maybe if it intravenous fluid like an IV bag counts, probably Tylenol does as well. Now we're changing from just kind of this definition here to the larger context. And we're in the coronary care unit at Bayonet Point Hospital, St. Petersburg, Florida. So this is real data, and this is for people who've had heart attacks, that kind of thing, or maybe they needed triple bypass. So pretty serious situations. They investigated the relationship between the number of factors per patient, X, so that's our explanatory variable, and the patient's length of stay in this hospital, Y, so the response variable. These days they try to get you out really, really fast. So it's interesting to see these as high as 12 days in the data. One person just 2 days. The data is given below. So remember, this is the coronary care unit. So we're imagining everyone who goes here, it's not for something minor. This is for potentially a heart attack that you survived or you're having something along those lines. One person has just 33 factors. That's kind of interesting. Stayed for 2 days though. The other person has 525 factors, stayed for 12 days. So this person went through a lot, poor person. And this is the same data now just as a scatter plot. Number of factors, the X variable is the horizontal axis, length of stay is the vertical axis. But just because there's lots of ways to say all this information, let's just remind ourselves that the number of factors, this is going to be the L1 input. This is the X variable, and this is the one that we call the explanatory variable. Again, we mentioned this a lot. This is, to me, what makes this kind of tricky. We have really 4 ways to say the same thing. L1 is just the 4th way. That's how you put it into the calculator. Likewise, just to get this all in line, L2 is this thing, which is also Y, and it's also called the response variable. First thing we want to do is calculate the least squares regression line. So this is the point at which we just start plugging things into the calculator. Any questions at the moment with just looking at the data and the context? Okay, let me get this imported. Oh, forgot how to do it. Let me try again. Kind of the nice thing about this problem is that this is like the major thing we've been doing all semester long, just importing data. Only difference is we have 2 variables we're plugging in. Okay, I think I've got L1. So it looks like 7 pieces of data for both columns. Anyone need any additional time? Okay, next thing, after we're satisfied with the data, hit the stat key. Go over to calculate as if you're doing standard deviation and that kind of stuff, but go down to option number 8. And once you get a hang of it, you could just press 8 on the calculator if you know exactly where you're going. It's a little bit faster. To enter through this menu, just ensure L1, L2 is printed here. If it's backwards, you'll have to reset it. That's something you could ask about during an exam setting, and I would be able to help out. And here's what it prints out. We have y equals a plus bx. I would write it out personally as y hat because that goes along with the formulas in the book. It reminds us that these are now a prediction line, giving us predicted values. Y hat equals a plus bx. Then the thing we actually write out is y hat equals, first the a value, we're rounding this to 2 decimal places. And I believe first one was blue for the intercept. Let's keep that order the same. To 2 decimal places, this is an intercept of 2.96. This would be a unit of days itself, because that's what y hat is giving you, predicted length of stay in days. Then the b value, well, this looks like it should be a positive slope. It's going up. The slope is positive here, but it's a very small number to 2 decimal places. You know what, let's change this a little bit. Let's go to 3 decimal places on this. I feel like the instructions made sense when I wrote them, but now that I'm looking at that tiny number, 3 would be a better idea. So sorry for the quick edit on this one. Feels like we're losing a bit of accuracy. We want really 2 significant figures, 0.0145 rounding up, plus 0.0145. Hang on, that's 4 decimal places. To 2 decimal places, it'd be 0.15. Sorry, rounding's hard today. Let me double check my numbers. If I'm going to 3 decimal places, I'm at that value 4. That would round up to a 5. I think we've got it. Does that look all right to folks on the rounding? Oh, let me double check my data with you. I should have double checked the scatter plot as well, but let me look into the data first. So 231, 113, 33, 525, 472, 78, 360. I think I did this one faster. So 9, 4, 2, 9, 12, 5, and a 6. So I think I've got the data in right. Let me double check the scatter plot. Weird. Yeah, sometimes when I check these numbers myself, I have a particular habit of putting in, like, say, a 213 instead of a 231. So let me look at it again. Let me know if you see any discrepancies in my data. This is one of the things that's really frustrating in my lab statistics. But if this was an exam question and you're pretty close on these numbers, you might not lose a point on part A. And then I'd use your equation to check your 5 further parts below.
Yeah, I see what I mean.
Awesome. These are really hard to double check, especially when I make a mistake here. It's my mistake, so it's like invisible to me. They're sometimes hard to correct. One strategy that helps, and this sounds awful, but if you can't find the error and MyLab Statistics keeps throwing out your answer, you can ask me about it and I'll check the system. Another thing to try is just delete it and start over from scratch. Sometimes that's the best thing because your own mistakes are the hardest ones to dig out here when it comes to just a cloud of numbers. But back to the calculate, option 8. Thanks for mentioning that. I have many times put in the data wrong, so I appreciate the double check. We've got the value for A and B and just throw in the X. for the full least squares regression line. Then if you want to, this is not a bad thing to do. Throw it on here just as a quick plot. If I was to plot this as best as I can, you know, these data almost seem like they'd be nonlinear, but we're treating them as linear in this problem. My line that goes through them would probably look about like something like that, maybe. A little leverage down there, a little pull up here. You never have to plot them exactly. I think this point down here feels like an outlier a little bit to me because it makes me want to make the line go a little bit different than a straight line. Yeah, about like that. That's about what my line would look like. You don't ever have to do that, but sometimes it's not a bad idea. Any questions at all so far? Okay, well, the calculator did a lot of stuff. You can see the official notes in chapter 7 about how all this gets put together. Next thing we're going to ask is, does it make sense to interpret the y-intercept? The y-intercept is that number 2.96. I feel like this one is a major judgment call. Here's what the steps would look like thinking about this one. A y-intercept always, whether it's a math class, a statistics class, anywhere you might be, it corresponds to where the other variable x is 0. But x is number of factors, so we have to ask ourselves, could you arrive at the coronary care unit at Bayonet Point Hospital? You have a massive heart condition, and somehow you have 0 factors. Does that seem reasonable? Some people shaking their heads no, and I would tend to agree. I mean, it sounds feasible. I mean, you could put in 0 factors, but if the insurance company is looking at this, they might say that's a mistake. No way. This is a specialty hospital. They treat major cases. The minimum value we had was 33, and this one looks weird already. It just happened to have 2 days, so it sort of fits the pattern. So I would say because of this context, and it did require a judgment call, we could say, no, it does not make sense. Because the y-intercept, I'll just abbreviate to y-int for intercept, corresponds to 0 factors, but all patients are in a health crisis. We expect many factors for every patient, pretty much. And that's kind of what we see in the data. There are 2 exceptions, the 78 and the 33. I feel like you could kind of go 2 ways on this. Maybe 0 factors could make sense. Maybe someone just got admitted and then had to go to a different hospital. Maybe it could make sense in that kind of way. So this is a tough one because it just depends on how you're going to justify it. There's always an explanation you have to put down below. So if you went a different way, if you said yes, but you have a convincing explanation, that would be for full credit as well. It's really all about thinking about the context, deciding if an intercept fits into the problem. And if you can justify it, you've done the spirit of the exercise. Either way, you've answered it. Usually they're not kind of on the fence though. Usually it's pretty much one way or the other, like on the last problems. Well, any questions at all, folks, on that one there? Yeah,
So when you're asking about the y-intercept,
Yes.
that's where the line will cross the y-intercept when x is 0.
yeah, it would cross in the y-axis. So the scale's funny because this point right here is not the y-intercept. That's just the window for the data, basically. So you would have a scale going all the way over here, vertical axis going this way. And does that make sense? That's 100. You know, actually, that would have been about 0 right there. It would have been about 0 here. So this would be where the y-intercept would have been here. Looks like this is actually 0 on this axis. So y-intercept would be right where it crosses vertically right here. Other questions about that so far?
So with that
Yeah,
being said, what, it's not zero then, right?
But I-
oh, yeah, good point.
Y-intercept is not zero now.
Yeah, the y-intercept would have been this value. It's about 2.96 coming down from this number, but it occurred with the x variable is 0 here. So that's the x equals 0 being plugged in right there,
Okay.
hitting the line, giving the 2.96 coming out. Does that make sense on that so far?
I mean,
Gotcha.
It does, but it like, to me, it like contradicts what we just learned, you know? Because if x is zero right there and you go up, what your statement says in B
Yeah,
does not make sense because the y-intercept corresponds to zero factors.
Yeah, if they stay for 2.96 days with zero factors, it doesn't make sense because they're in a healthcare unit. So if like bedpan and their IV and the needles are all factors and they had millions of them, like they literally walked in, stayed for 2 days and left.
Oh, I get you.
yeah. I know one way to think about this is if you walk into just about any hospital, they're going to put a little risk tag on you. That's one factor already. So 0 factors, well, it would say 2.96 days you would stay, but it just didn't fit in the context, is what the problem was for this problem.
I just keep getting mixed up, so I apologize.
Oh, no worries at all. It's, again, lots of stuff to put all together all at once. Thanks for asking these questions about it. Other questions at the moment? Okay, so again, thinking about this, the y-intercept corresponds to the x variable being 0, but then the x variable is the number of factors. So then you would go to number of factors, find the 0. It was right on the intersection here for this one. Usually that's not the case for most problems. It intersects on the vertical axis at 2.96 days, but that's just what the number was, 2.96 right here. So yeah, it's like jumping through lots of hoops. There's lots of stuff going on with just one problem like this. So that was the slope one, or excuse me, the y-intercept one. Next is the slope. This one's tricky in a different way. Intercept's tricky because you have to think really hard. Does this fit the context? Could this even happen for x to be 0? Y-intercept's hard just because it's a whole structure that you're putting together. So let's go back to the chapter 7, shouldn't have closed that out. Like we mentioned, just to emphasize the strategy, let's do a quick copy paste on this. That was too far. Let's copy from here down. Here's the major part of the strategy, this step. Let me just delete to this point. Let's kind of undo all of this. Put a little blank here as well. Okay, so this part goes to this part as well. And you know, I have a change of heart on this. Just make this as similar as possible. I want to put in a little blank here as well. This is a reminder that this is a part that we filled in at the same exact time. Okay, anyone need any time writing out all that? That's quite a bit of stuff that to put down. Okay, let's take just a mental breather as we look at this. You know, the first battle here is you have to say what is the slope in the very first place. The intercept for y is not bad if you remember x is 0, because if you're plugging 0 right here, it deletes this whole number and it's just 2.96 for the intercept. But you have to remember that the slope is always this part right here. So that part's the slope. That part, the 2.96, is the y-intercept. So we start by just saying slope equals 0.015, and we make it over 1 with a huge fraction bar. Then we go back up to right about here, and we look into what are the variables themselves. So we have to take this information, import it down, and write in the units. Anyone see what the unit should be for the numerator, the one up top?
With the what?
What should be the unit for the top port of the slope? Absolutely. It's always the response variable, the length of stay. So whatever is y, your response, or going in the vertical direction this way, you will say that's the unit for this. So length of stay in days. Now let's put it in the reminder just from the last notes as well. The numerator, or the top, is always response y. If you get the top down, there's only two things, right? If you have the top down, it nails what the bottom has to be, just the other variable. So the strategy is memorize what goes in the top. This is good stuff for the notes as well. Exam 3 is open notes like exam 2. Put in explanatory X. And even though the exam is open notes, the more you can memorize before the exam, the more you can just organize in your head, the lighter the cognitive load. It doesn't feel like as big of a problem anymore. It's kind of like driving a car. If you remember when you first learned to drive a car, there's a million things you had to pay attention to, and then everyone is annoyed with you because you're worried about weaving too far left and right. But the moment you write this out and do it a few times, several times, it becomes automatic eventually. So memorize this part. The horizontal axis, x variable, will be one factor. And now this is saying, for an interpretation of our slope, let's actually draw it out here on our plot. Anywhere you go, I just pointed to 200. If we increase this by one factor, that's kind of hard to draw, so I'll exaggerate a little bit. That's more than one. We go up by 0.015 days for the length of stay. Again, kind of exaggerated because that's a hard amount to go up by. And this is a 200 to 300, so hard to go just by one. But that's the idea. All we do now is we just write this in as we see it. For each point increase in factors, so that's when we go horizontally, we go up. So the response is the length of stay we just take whatever the direction is or the sign is from here. If it's positive, we'll say increase by whatever the slope is. So we just state the value 0.015 days. If you left off the unit here, I wouldn't think it's a big deal, but it's probably just flows better if you say it in this last spot. So for each additional factor, the length of stay at this hospital is increasing by 0.015 days. Not by much, but again, hundreds of factors go into the care in this hospital. Well, that's the third look into the slope. It's tricky each time you look at it. Doing this as a homework problem, what I would encourage is, before you even look into the multiple choice question, do it like this, and then it's going to be way easier to answer the multiple choice question. And then it's doing kind of two things at once. You're practicing for what it will look like on an actual exam setting and just moving through the homework question in MyLab Statistics a lot faster. It'll look just like this as a quiz as well. So you'll have a practice on quiz 7 before you do it on exam 3. Well, that's pretty intense. That's what's kind of nasty about chapter 7. Lots of concepts are going together. Honestly, I think chapter 13, when we start doing inferential statistics, it's not as bad as this. You get a formula, you just plug in numbers. But this is thinking in terms of like 4 different things connecting into one concept. an equation with two parts that have very different modes of interpretation. And parts B and D that we just solved, I don't know where part C went. This is a little bit out of order. Let's just keep it the way it is. Sorry for the disorder. These are like the hard parts, doing these kind of interpretations. Rest of it is not so bad. So let's take a look into part C, just as kind of a break after those. Any last questions at all before we go off to the next part? Okay, it goes on to say, suppose that a patient at the coronary care unit at Bayonet Point has 435 factors. Use the least squares regression, referring to this y hat equation above, to determine the predicted length of stay. And you might look into the data. Closest neighbor was 472 factors at 12 days. We expect an answer that's in the neighborhood of 12 days. So if I got 3 days or 40 days, we're way, way off. Should be around that value. So first thing we'll do is copy the first part of the equation up to x. X is going to change into 435 factors. So it'll be y hat for the predicted value equals 2.96 plus 0.015 times 435. So 435 is x, and x was in that spot. We're just making a quick substitution. Now this is not so intense. This is just filling out a formula essentially. I have in the calculator 2.96 plus 0.015 times 435 factors. It goes up by 0.015 days for each factor. So this is a lengthy stay, it looks like. And it came out to 9.4 days. That was in the neighborhood of the 12 days in the real data. So 9.4, let's round a little bit better. That would be 9.5 days is the predicted length of stay. Well, any questions at all, folks, on the 9.5 days? Awesome. Definitely feels like after you get parts past the intercept and the slow part, it's kind of coasting from here. The residual is a little bit trickier. This one has a formula as well, so it's a little bit more direct as well than the other ones. Calculate the residual for 360 factors. For this, you'd want to look into the data table. We have 360 factors here, having a length of stay of 6 days. Let's bring this down just as a reference. Oh, first thing you'd want to do definitely is just write down the formula for the residual. The formula goes E equals, it's always y minus y hat. The role the variables play is just as important. Y is observed. Y hat is the value that was predicted. And notice the wording in part C is also mentioning predicted as well. Y hat is always the predicted value, so it just means you're using something like this. But this is a trickier problem than it looks on face value. Part C gave us a predicted value, but that was for 435 days. We've never found the predicted value for 360. Oh, excuse me, I said that in a weird way. The predicted value y hat was for 435 factors, not days. That person would be in the hospital a long time for that long. So we need to first, as a step one, find y hat for 360 factors, because that part hasn't been done yet. It goes like this half the time in the homework. Other times it might use the part C and say, find the residual for 435 factors. That would have been nice, except 435 factors isn't in the data. There's no observed value that goes along with it. And you have to have an observed value in order to do a residual. So here's our step one. We go back to y hat again. Y hat is 2.96 plus 0.1015. We have 360 factors this time, so throw in 360 factors here. But if we've done it once in the calculator, we've done it as many times as you like, just hit up arrow, enter to drop down that same formula, override with 360, and it's even faster than before. At 360 factors, this patient is staying for 8.36 days. So y hat equals 8.36 days. Now, step 2, find y. That's just as big of a deal of this problem as well, because it can be confusing. What is y? The way we find the y value on this one is we look into what the number of factors were from the explanatory variable, and we want that entire row here. Well, really just one part. This is the y value. So we have here y, the actual value observed in the data corresponding to the 360 factors, is 6 days. A lot different than the 8.36 days. Step 3, use the formula. In other words, we're just putting it all together. We cited the formula so we could see what the moving parts were. We calculated each part as necessary. One was just a table lookup. Now, finally, the formula is E equals y minus y hat. Plug it in. E is equal to 6 for y minus y hat. It's in step 1, 8.36. So go 6 minus 8.36. And we get a value of negative 2.35. So that's our residual value so far. There's a kind of a check to this once you get the value out. Any questions at the moment before we look into the additional check? Okay, so here's what the check would look like. Go back to this plot here. Let me erase this little bit we put in. We try to draw the regression line as best as we could. It's not perfect, but it'll do the job. Let's drop it down below right here. So if this makes sense, we should be able to go to 360. There's 360, and there's the y value right in this spot. So, well, that's really a pair of points, but this is the observed value. We also have a y hat value. That was the 8.36 days. And that's just going to be the point that's on the line itself. That's over here to the left. My line's not perfect, so I'm just going to imagine slightly higher. That's 8.36. This is the predicted. The fact that we got 6 minus 8.36 and negative 2.35 is just telling us the value that we observed is lower than the value we would have predicted. If we got a positive value, then this observed value would have been above the regression line instead. So it goes in this kind of way. Negative here means the observed value is below the regression line. Well, that's the wrap up on least squares regression. It's a pretty intense topic. The idea is just to try to model data, make predictions. Y hat is the prediction, but a lot goes into interpreting all these different moving parts when it comes to the regression line. This will come in as an exam 3 question. As far as the final exam, it's kind of a hit or miss question. Half the semesters it makes it on, other half of the semesters it doesn't. The final exam can't involve every single problem in the entire semester, so it's one to definitely be prepared for. It's not a guaranteed problem. Any last questions or comments at all before we finally close out chapter 7? Okay, chapter 6, chapter 7, they really kind of go together. The whole purpose of chapter 6 was to get us into chapter 7. But at this point, we're switching gears in a massive, major way, which is kind of exciting. The very first part of the semester, we kept talking about inferential statistics, and it's going to start in earnest in our chapter 13 here. We mentioned chapter 10 is the kind of the bridge connecting the ideas. We're not covering a ton in chapter 10. There's no MyLab assignment that goes along with this one. I felt like the questions that were being asked there, we're just going kind of far afield for what we're trying to do in chapter 10. It still says to read chapter 10, but think of that as kind of just light reading. There's a lot of information there. But we've got it pared down to just several concepts contained in this page. We'll talk about the simple random sample design. We'll talk about observational studies, experimental studies. The book goes into a lot of detail on all these different kind of topics, different sampling designs, other definitions with experimental design. But since it's introductory statistics, and the last of the course is really going to be focusing on this, that's where we're going to focus on as well. Simple random samples, what it means, how to obtain one, and just the difference between an observational study and experimental design. We'll need to know that difference to make the right kind of conclusions. So some information that we're going to take a look in just as a reminder is when we say population, we mean the entire collection of everyone we're looking into studying. A sample is just a small part of that population that we really want to study. And when we take a simple random sample, this is the new definition, and it's actually really kind of tricky. N is referred to as the sample size, so we've been using that quite a bit throughout the notes already. And a simple random sample of size n is a sample that does one thing. It's a sample selected from a population in such a way that every different possible of the same size n, so if n is 10, every other sample of the same size 10 has an equal chance of being selected. No biases whatsoever. Every possible sample at that sample size has the same equal chance of occurring. A simple random sample is highly representative of the underlying population at reasonable sample sizes. So if you take a sample size of 1, that's not reasonable. That's not a random sample. It becomes anecdotal data. So we're avoiding that for sure. N equals 1 is anecdotal data. What I mean by that is maybe I'm taking a new medication. Maybe it's, let's say, a sleep medication. And I tell all my friends, I took this drug, it worked really well, you should take it too. That doesn't really work that way, unfortunately. I have my own particular metabolism biology. If it works for me, who knows if it works for anyone else? And maybe it was just a placebo effect in the first place. Anecdotal data is not helpful at all, really. It might help us form hypotheses. What we want is something bigger, like not quite n equals 2, that's kind of awful. But some studies can be done as small as samples as n equals 4. It just depends. When we have a small sample like n equals 4, there's going to be a lot of errors in the prediction we make, but we're definitely avoiding anecdotal data. This is not a random sample. Better sample sizes start to hit a sweet spot around 30 for reasons that we're going to discuss later on through something called a so-called central limit theorem. This is not saying a sample size at 5 or 10 is bad. It has weaker power for making strong conclusions. But something really incredible happens at a sample size of 30. And just for a preview of that, this finally answers the question of why did we care about the normal distribution? Well, the normal distribution comes in surprising ways for the central limit theorem, where statistics are distributed through the normal distribution We're gonna look into the sample proportion, p hat, as well as the sample mean, y bar. The normal distribution just shows up unexpected in the most random kind of way. When it comes to sample means, this is a nice sweet spot for a sample size. But we'll look into more about collecting a simple random sample. We'll actually simulate it using Excel when we come back a little bit more fresh next time. This example has a lot of white space, so I have a lot to say on this one. But this is the first bit of what the topics are going to be about in chapter 10. Then, after a short stay here, we'll be moving into chapter 13. Chapter 13 is big. It's one where it's really helpful to take a look into the reading before you come to class, even if you're just skimming through. It'll kind of set up things in your mind so you can see how things connect together. But any last questions at all, folks, before we call it a night today? Just a few minutes early. Really, that's 4 minutes this time. Okay, well, we'll come back to this on Thursday. Quiz 6 will be due Thursday as well, so if you have any questions on that one, don't hesitate to ask. Otherwise, I'll see you all tomorrow.
Seven's not 100% on.
Yeah, the problem just like the one we just did,
Okay.
that additional example.
Got it.
I think I figured out how I was getting so mixed up.
Oh yeah, on the, was it the slope ones or, no, it was the intercept one, I think.
Yeah, if you go back to,
This one here?
yeah, so you see how you have your y-intercept
Yeah,
for 2.96, and then down here, we got the response y variable. In my notes, I wrote that as y. Does that make sense? Like I put slope right here,
yeah.
and I put y over x.
Oh, I
Right.
see.
I didn't put y-intercept on that, so I was putting the wrong number and then it was fucking me up.
Gotcha,
Does that
yeah.
make sense?
It does, absolutely.
So I was looking at my notes. I'm like, but he told me that was y, but
Yeah.
it's the y-intercept
Exactly, yeah.
where it crosses the actual.
Yeah, that vertical axis. And that's the thing that's tough about this. There's like, they really count the different ideas. There's like dozens and dozens of little tiny things to keep track of. Just looking at the axis, there's this 4 concepts going this way, 4 concepts going this way as well.
But when you think of slope, right, like, and it goes for anything, when you do slope, it's rise over run, right?
Yeah,
So
y over x,
over
yeah,
x. And so that, that's just what threw me off. The
gotcha.
y-intercept is what it is.
Exactly. So when you're thinking y-intercept, you switch to the other variable, x, forcing it to be 0.
And I just did, it just wasn't, it didn't click and then it did,
Awesome.
but it's, I don't know if it's OCD, but it was like really bugging me.
I'm kind of the same way. If there's something that just doesn't make sense, everything else depends on it. It feels like I can't move forward to understand the other stuff.
Right.
You got to resolve it down there first before you move on.
And I felt bad. And then the way she explained it, she was like, it's about the factors. Like it instantly made sense, right?
Yeah, she's thinking more in terms of the context, but you were more about the mechanics of it.
Right, but that still helped like piece it together
Gotcha,
a
awesome.
little bit. Cause it was like, and I don't know if she got clear on it, but yeah, it was like muddy as hell.
Yeah.
And I also do think I was overcomplicating it, you know?
Mhm.
I really do. So, but thank you for your time and your effort, man. I appreciate all you
Yep, absolutely. I appreciate your hard work as well.
do. Have a good night.
You too.